Welcome to this educational video on Henry's Law, a fundamental principle in chemistry that describes how gases dissolve in liquids. Today, we'll make Henry's Law simple, showing exactly how it works with clear visuals and examples. Let's start with a clear statement of Henry's Law. For a gas dissolving in a liquid at equilibrium and constant temperature, the partial pressure of the gas above the liquid is proportional to its dissolved concentration. Mathematically, we can write this as P equals K sub H times C, where P is the partial pressure of the gas, usually measured in atmospheres, C is the concentration of the dissolved gas, typically in moles per liter, and K sub H is Henry's constant, with units that depend on the units chosen for pressure and concentration. Let's visualize what Henry's Law actually means. Imagine we have a sealed container with water and some gas molecules above it. The gas exerts a pressure on the water surface. According to Henry's Law, this pressure determines how much gas will dissolve in the water. As gas molecules dissolve into the liquid, they reach an equilibrium. The rate at which gas molecules enter the liquid equals the rate at which they escape back to the gaseous state. At this equilibrium point, the relationship between pressure and concentration is governed by Henry's Law. Double the pressure, and you'll get twice the concentration of dissolved gas. Henry's Law can be written in different ways, depending on what we're solving for. If we want to find the concentration, we can rearrange to get C equals P divided by K sub H. Or if we need to solve for K sub H equals P divided by C. You should choose the form that's most convenient for solving your specific problem. Let's talk about units and typical values for Henry's constant. If pressure is measured in atmospheres and concentration in moles per liter, then Henry's constant has units of atmospheres times liter per mole. The value of Henry's constant varies with temperature and depends on the specific gas and liquid. For example, for carbon dioxide in water at 25 degrees Celsius, K sub H is approximately 29 atmospheres times liter per mole. Gases like oxygen, nitrogen, and methane have different Henry's constants, reflecting their different solubilities in water. Henry's Law has some key dependencies that are important to understand. First, temperature significantly affects gas solubility. As temperature increases, Henry's constant typically increases, which means the solubility of the gas decreases. This is why hot water holds less dissolved gas than cold water. If you've ever noticed that warm soda goes flat faster than cold soda, this is why. Second, the presence of dissolved salts or other solutes in the liquid can affect gas solubility, often reducing it. This is called the salting out effect. Let's solve a simple example problem using Henry's Law. Our question is, what is the concentration of oxygen dissolved in water if the partial pressure of oxygen is 0.21 atmospheres and Henry's constant is 769 atmospheres times liter per mole at 25 degrees Celsius? We'll use the formula C equals P divided by K sub H. Substituting our values, C equals 0.21 atmospheres divided by 769 atmospheres times liter per mole. Computing this division, C equals 2.73 times 10 to the negative 4 moles per liter. This low value explains why fish need specialized organs like gills to extract enough oxygen from water. Oxygen simply isn't very soluble in water. Let's explore a common real-world application of Henry's Law: carbonated beverages. When a soda bottle is sealed, carbon dioxide gas is under high pressure above the liquid, typically around 3 to 4 atmospheres. According to Henry's Law, this high pressure causes large amounts of CO2 to dissolve in the soda. When you open the bottle, the pressure suddenly drops to atmospheric pressure, about 1 atmosphere. With this lower pressure, the solubility of CO2 decreases. The excess dissolved carbon dioxide escapes as bubbles, eventually making the soda go flat. Mathematically, the CO2 concentration decreases proportionally as the pressure decreases, exactly as Henry's Law predicts. Henry's Law has many important applications in various fields. In environmental science, it helps us understand gas exchange between the atmosphere and bodies of water. For example, as ocean temperatures rise with climate change, the solubility of oxygen decreases, potentially threatening marine life. In medicine, Henry's Law explains decompression sickness, or the bends. When divers ascend too quickly, the rapid pressure decrease causes nitrogen to come out of solution in their blood, forming painful and dangerous bubbles. In industry, Henry's law guides processes like carbonation, water treatment, and gas separation. Before we wrap up, here are some quick tips for working with Henry's law. Always check your units. Make sure the units for pressure and concentration match the units of Henry's constant. Use the correct Henry's constant for your specific temperature and solvent. And remember that higher pressure means more gas dissolved. The relationship is directly proportional. To summarize, Henry's law provides a powerful tool for understanding gas solubility. By stating simply that pressure is proportional to concentration, it helps us predict how gases will behave in countless real-world situations. Thank you for watching this explanation of Henry's law.